Nope, can't mention the guillotine. All right, guys. Space. Oh yeah, now it's on there. All right, so. All right, so yeah. Well, what are the basic steps? Solve an optimization problem. Diagram and label, right? Then what? You need a formula. How do you know what you have to write a formula for? Just anything? Yeah. Whatever they're asking you to maximize and minimize. Okay, then what about that formula? Yes, Manny. Yeah, you got to get it in terms of one variable, which will require a lot of times the second equation to solve for another variable and then substitute. That's how you get your primary equation in terms of one variable. So now you have an equation, one variable. You want to look at it and say, for what values will that variable make sense, right? You want to have an idea before you get your answer. Okay, what should the answer look like? Maybe if it's a length, it shouldn't be negative, etc. But then comes the fun part. So you got your equation in one variable. What do? Okay, after you get the interval, though. What are we going to say, Jen? Yeah, max-min technique. So you're going to get the derivative and use your first or second derivative test. Find your max, find your min. We love it. So those are the basic techniques. You got it? Got a sense. Okay, do you want to do, I know you wanted to do the question 13, but did you want to see any of those other ones? 13 is the big one. Who knows the answer to 7? Anyone have an answer for 7?
Yeah, it was fractions.
Manny, we're going to ask something? Okay, 7. Let me just see what that was. And then we'll do the 13. Nope. Let me see. I don't want to do too many because I want to make sure I get to the can, but we could see what we can get done here. Oh, 3 was just, I'll do 3 really fast because that's only takes a sec. 3, it said, what is the smallest perimeter possible for a rectangle whose area is 16 square inches, and what are its dimensions? So you have a rectangle. So I'll say y and x. Okay. We want to get the smallest perimeter. So we need a formula for perimeter. So in this case, what would the perimeter be? Well, in this case, it would be 2x plus 2y. Yeah, I like to mix it up. Okay. Consistency is not a human trait. But all right, the kids. All right. That was. I don't know if we'll do any more homework. They gave us that the area was 16 square inches. Do you see that that's going to give us our second equation? Yeah. Yep. So what's the secondary equation that's going to give us? Nope. Sorry, no one heard it. They just heard nope. They have no idea what I was saying that to. So x times y equals 16, right? The area was 16. Okay. So you solve for one of the variables with that. Which one you want to solve for? It doesn't matter. Okay, so y equals 16 over x, right? You put that into the other one for your y. So your perimeter equals 2x plus 2 times 16 over x, or 32 over x. For what value of x is this going to make sense? X has got to be a number, it's a length. Yeah, it's going to be greater than 0, so just note to self, don't come back with a negative answer, or you're going to get fired. Okay, and then you just get the derivative. 2, now that's 32 over 32x to negative 1, so 2 minus what? Minus 32x to the negative 2, or over x squared. So we don't want x to equal 0. The derivative wouldn't exist, but we didn't want x to equal 0 anyway. We knew it had to be greater than 0. So we want to find out when this is equal to 0. When you're trying to solve that, you know, it's nice to take the negative term and just bring it to the other side and then cross multiply. Right? It's a nice idea. It's one way to do it. So 2 equals positive 32 over x squared. So 2x squared equals 32. X squared equals 16. And now normally we would say x equals plus or minus 4, but in this case x has to be greater than 0. So x is 4. And we want to make sure that this is giving us a minimum perimeter. So I would just like to make a little sign chart, like doing the first derivative test. Or do you like the second derivative test better? First is nice, right? It starts out at 0. What's that? I know. You guys like the first derivative test. Where is my first derivative? Here it is. Okay, so you pick a number like 1. Is your first derivative 2 minus 32 over x squared positive or negative? What? Negative. All right, you take a number like, how about 8? So p prime of 8, this is p prime of 1. And at 8, that would be positive. So do we have a max or a min? Yeah, so we do have a minimum perimeter. And they said dimension, so when x equals 4, and if x equals 4 and xy equals 16, what does y have to equal? 4. So they're both 4s. Got it? Those are fun ones. Okay. Wait, what was 9? Let me just see what 9. Was 9 the other one you wanted to see? 7? Oh, the box one, 8 by 15. Okay. We want the greatest volume out of an 8 by 15 sheet. So you guys all seem to, like, you showed me your work for that. You just, the math just went ugly. Probably when you got to quadratic formula. I don't know if this one factored. So you had a sheet that was 8 by 15 inches, I believe. You have an X and an X. All right, get it up. When you fold up the sides, because we're trying to maximize the volume is going to be length times width times height. What's the length going to be? 15 minus 2x. It was 15 the sheet, but you cut out an x out of both sides, so it's 15 minus 2x. And the width? 8 minus 2x. And then the height? X. Good. So the nice thing with this box problem, it was already in one variable. So we didn't even have to worry about that. We just got to clean it up a little. So we're going to distribute, and then we'll multiply by the x. We'll just multiply these two out. What's 15 times 8? So we have 120. We have a minus 30x and a minus 16x. Can I combine them? Minus 46x plus 4x squared. We got to multiply through by the x. So our volume, can we change the order? You guys are the best. All right, so what's it going to be? 4x cubed plus 120x. Okay, now we'll take the derivative. Ooh, there's always some kid that sets that equal to 0. Every time. Oh, right? Is it really? I got one. Emily did it. Somebody did it. I did something. Now I'm at the good part. Nope, not yet. All right, so you're that kid. All right, what's the derivative? Is this what you did? Okay. I'm sorry. We said 12x squared, 92x plus 120. Okay, well, that's always defined. Yeah. Oh, by the way, what are the restrictions on x? X has got to be between, it's got to be greater than 0, or we won't have volume. And you could include these. And less than half the smallest side, so less than 4. You're cutting out 2 of them, right? Alrighty. Does anything go into every one of those terms? 4. So we have 3x squared minus what? 23x. All right, I believe that. Plus 30 equals 0. Yeah, we didn't do the quadratic formula. That's no problem. So I knew this was going to be where it was going to end up. Oh, I'm sorry. So here. Okay. So. Oh, because the shorter side of the paper was originally 8 inches, right? Right. You're going to cut an X out of both sides of the paper, right? Like you could cut a 1 inch and a 1 inch, and that would leave 6 inches left, right? Or you could cut 2 and 2, and that would leave 4. Or 3 and 3, that would leave 2. Once you get up to 4, if you cut 4 inches off this side and 4 inches of this, you don't have anything left. So it's always got to be between 0 and half the shorter side with the box problem. With the box problem. So x equals negative b, 23, plus or minus the square root, b squared minus 4ac. You don't need the negative in there. You're squaring it. But minus 4 times 3 times 30 all over 2a. And one of these answers is probably not in the interval between 0 and 4, and one is, right? It's just like the one we did the other day. I don't feel like doing the math. You guys can have to tell. Okay, so one of them is x equals 6. It's got to be point something, right? So what, one is x equals 6.5. And what's the other one? 5/3? Okay. Okay, and this is the reject guy, right? This is the reject guy. Because it's greater than 4. Remember, x has to be between 0 and 4. So we're not even going to consider them. What's that? We making fun of my... Oh, okay. Oh. No, he's out. So we're only looking at the volume for values of x from 0 to 4. Like, if you really only have to look in there. We're going to look at the 5/3. Now, that derivative, which is over here, let's just say that it's positive over here, negative here. Let's just say you took a value like 1 and you plugged it in here. That's positive. And you took a number like 2, and okay, that would be negative. I believe that to be true. I have to. So we have a maximum volume, and x equals 5/3. Right? Oh, look, I'm boring the kids. Sorry. That was fun. But now the poster problem, that was fun too. The poster problem, and Ellie was very, very close. Melissa had it. I mean, I think this class, you guys were like right there. No, she doesn't know how she got it, but that's all right. All right, so here's the thing. You're making these posters. You're trying to minimize the amount of area that you're going to be using to make this poster. And this poster has some printed material inside. Now, the margins on the side are 2 inches. And the top and bottom, they're 4 inches. The printed material is all in here, right? And the area of the printed material is 50 square inches. Now, what you want to minimize is the area of the overall poster. So let's give this dimension, because I'm going to need to minimize the area of the paper. I think I would just want to call this whole dimension something. You want to call this x? Okay. And what about this dimension? Knew it. Okay. So we're trying to minimize the amount of area, so we need an area formula for this. That's just x times y. Is that all right? All right, that's good. But then it's getting it in the one variable. So we need another equation. What can we use to write a second equation so we can substitute? There's something else we know. What's the number that they gave you out of nowhere that just pops out? The 50. Okay, so let's figure out what equals 50, because that's the area of the printed material. If this whole length here is x, and you got 4 up here and 4 down here, so x minus 8 would be this dimension right here. So x minus 8 times, the other dimension would, you're right, it would be y minus 4, has to equal 50. Right, the area of the printed material. So what we're going to do is we're going to solve for either x or y. What do you want to solve for? All right, so we're going to solve for y. So let's get this x minus 8 out of there. Let's divide both sides. So y minus 4 equals 50 over x minus 8. Then what? We want to solve for y. Add the 4. So y is equal to 50 over x minus 8 plus 4. And that's what we're going to put in for y in our primary equation. So it was 50 over x minus 8 plus 4. All right, let's distribute, clean it up a little. Oh, we got an equation in one variable. We'll just take the derivative and do our little test. So we have 50x over x minus 8 plus 4x. That's the area. For what values of x is this probably going to make sense? Can x be a negative 3? No, because it's the length of our poster. Yep. Oh, yeah, because if x was 8, then we wouldn't have any printed material. Oh, that's smart. Oh, so really? Wow, you know what? That's the first time this came up today. So really, x is going to have to be greater than 8. Smart. Yeah. Well, because you've got a margin, x is composed of the margins, which have to be 4 inches each, and this dimension of the printed material. So x has got to be a value greater than 8, or else you won't have anything left for here. Just think of this dimension getting really small. It's still going to have to at least be 8 for the margins, right? Oh, I love that. Okay, so note to self, x has got to be greater than 8. Nice job. That was. Alrighty, time to take the derivative. Let's do it. What? Oh, no. Yes, it does. Are we afraid of the quotient? No. Lowity high, x minus 8. You'll be embarrassed you whined about this one. D high is 50. I don't know what you guys are talking about. That's high d low, that's just all over the denominator squared plus 4. Oh boy, oh boy. Look at that numerator. Look at that numerator. You want to cancel the x minus 8? That is not allowed, because it's not, x minus 8 is not a factor of the entire numerator, only of the first term. Well, then what are we going to do? I'm just going to leave it? Let's distribute. So it's 50x minus 400 minus 50x over x minus 8 squared plus 4. Oh, see? The 50x's cancel. Now this derivative is adorable. So our derivative is just negative 400 over x minus 8 squared plus 4. Oh, yeah. Would you want to add the 4 to? Well, we know we don't have to worry about where it's undefined because it's undefined at 8, as Cameron said, x has got to be greater than 8. We don't have to worry about that. So let's just find out when it equals 0. Let's find out when negative 400 over x minus 8 squared equals, oh no, I'm sorry, plus 4 equals 0. Let's solve that. One thing, like you're going to see with a lot of these problems, and I might as well just tell you, you're going to have a negative term plus a positive term equals 0. A nice thing to do is bring the negative term to the other side, so everybody's positive and cross multiply. Yeah, we're adding the 400 over x minus 8 squared. It's just one way to do it. So we have 4 equals 400 over. You see how nice that is? And we're going to cross multiply. So we have 4 times the quantity x minus 8 squared equals 400. Oh my goodness. Then what? Let's just talk in language. So divide by 4x minus 8 squared equals 100. There we go. So normally we would say x minus 8 equals plus or minus 10. Right? We'd have 2 equations. Yeah, this is not going to be good for one of them. So you have x minus 8 either equals negative 10 or x minus 8 equals positive 10. Yeah, because this one would give us x equals negative 2. Wah, wah, reject. Because remember, x has got to be greater than 8. All right, so the other one gives us x equals 18, right? So now, just got to make sure if we make x 18, well, first of all, it asks for dimensions. Let's just make sure that gives us a max. What were we looking for anyway? Oh, minimum. We were looking for a minimum area. So if we look, here's our A prime right here. So I'm just going to make a little A prime sign chart. It couldn't even exist for values less than 8. I don't even have to worry about that. I just want to make sure at 18 that that's a max and not a min. So give me a number that's in between 8 and 18. 10, okay. If x is 10, 10 minus 8 is 2, you square it. What's that first term going to be? Negative 400 over 4, so negative 100 plus 4 is negative 96. You take a number greater than 18. Sure. Okay. You have 20 minus 12 squared, negative 400 over 144 plus 4. Oh, that's positive. So we have a minimum area when x equals 18. Oh, no, how would we get y? Yeah, we have what y equals in terms of x. What does that make y? 9. Because y equals 50 over x minus 8 plus 4. That's fun, right? Okay. All right, now we got to get right to the soda can problem. So forget about example C. I threw that back in there again. I don't know why. But this one that's important is this one. Forget about this one. The can problem. Okay. Well, there's certain classics, but it can be applied all different problems. But I try to focus on some of the more classic problems. Okay, here's the thing. You ever sit around with your friends drinking a soda and say, wow, I wonder when they made this can. If they used the least amount of aluminum possible, or they just wasted and waste all this extra money. So that's what we're going to try to figure out today. And we're going to be using a real 12-ounce can of soda, which happens to contain 21.6562 cubic inches of soda. So we know the volume that of soda that it houses, right? This is a tasty. Oh, this is. I got this out of the recycle container. Miss Barris chucked this. I was like, "Ooh, good! I forgot my can today, and she had one. So yay!" All right, but what we want to do is we want to figure out what dimensions are going to minimize the amount of surface area, minimize the amount of material used. So we've got a diagram already here, thanks to me putting this on here. You have this right circular cylinder, you have the radius, and you have the height. Those are the dimensions of one of these cylinders. What we're trying to minimize surface area, right? So we need a formula for surface area. Surface area is just the sum of the areas of all the surfaces. So when you're talking about a can, you got the top. What shape is that? Circle. You got the bottom. That's another circle. Then you got the sides. Now, forget about the top and the bottom. If I took scissors and I opened it up, do you see that the sides, if I opened it up, would be a rectangle? You do. All right, so we got the sides are going to be a rectangle. So we need a little more info before we start doing calculus on this. What's the area of the circle? Pi r squared. So we have a pi r squared plus a pi r squared. That's that area. All right. Now, to get the area of the side of the can, we're lucky. We know that this dimension is the height of the can. And before I opened it up, if I keep it back together, what is this length around? Because that is this length up here. What is the length all the way? Circumference. You guys know the formula for the circumference of a circle? Pi d, and d is twice the radius. Now don't add any squares because it's a length. I want on 2 pi r. So like this side is 2 pi r. All right, let's see. The diameter is just twice the radius. They said that the circumference was pi d. All right, so the surface area is equal to 2 pi r squared, because you have a top and a bottom, plus the area of the sides of the can, which is 2 pi r times h, right? Because it's just length times width for the rectangle. Oh, great. So we have our first equation. This is the equation we're trying to optimize. We're trying to minimize surface area. But what's the problem? Yeah. But as far as the process that we've been going through, like the box problem, we didn't have any problem, but the other problems we've seen, look at this. What are the variables that we've defined the area in terms of? R and H. We want to get that H out of there, right? Or the R. I mean, it doesn't matter. I don't want to play, favorites, but so we need another equation with an R and an H in it so we can solve for one in terms of the other. Is there any other information that they gave us that we can use to write a second equation? The volume. The volume of the soda contained in this can is 21.6562. Let's move the whole thing. Okay. So something is equal to 21.6562. That's the volume. The volume of a right circular cylinder is just made up by multiplying the area of the base, a circle, times the height. What do you think the volume is going to be? The formula for the volume of a cylinder. Just take the area of a circle times the height. So it's pi r squared times h. I love it. Alrighty. So what are we going to solve for? R or H? Okay, I'm not listening to you. H. I just pretend I don't hear the bit. But it's not that it's wrong. You could still do it. Just, never finish. All right, so we're going to substitute in for h 21.6562 over pi r squared. Yep. So we've got the area is 2 pi r squared plus 2 pi r times 21.6562 over pi r squared. Yowza. Look at that. Any cleanup to be done before differentiating? What can you do? You know, nothing. You can get rid of the pi and the r out of this second term, right? This pi up here cancels there. This r cancels, so we still have one left. And so the area in terms of r is equal to 2 pi r squared plus 2 times 21. Shoot, I did know it at one time today, but I forgot. It was 43 point something. 43 point. Oh, I need the cap. Then it's going to just be over 0.31 what? Thanks. Over r. I wish we could hold up the bells. Now we're just going to take, also the radius, do we all agree would have to be greater than 0? Okay, that's a little greater than 0. All right, we're going to have to take the derivative and set it equal to 0. We're going to have a positive and negative term because a prime equal to 4 pi r. Remember this r down here, that's like times r to the negative 1? So we're going to have minus 43.3124 over r squared, because it's going to be to the negative 2. And we already know that r can't be 0. So we set our derivative equal to 0. We're going to bring the negative term over to the other side. So we have 4 pi r equals positive 43.3124 over r squared. All right, we're trying to find out where the derivative equals 0. Now, probably won't be able to finish, but if you cross multiply, we have 4 pi r cubed equals 43.3124. You're going to divide by 4 pi and take the cube root. It's very exciting. It is. Do you think that this can is optimal? No. When you solve this, and I know you're going to want to do that at home, you're going to find out it should be like this tall, like 3 inches tall, and should have a radius of 1.5, so like 3 inches like in diameter. So it should be shorter and fatter. They're wasting aluminum doing this, but it fits in your, because look how it fits in my hand. If it was, like that, it was fatter, I might be like, whoa, might be hard to hold it up. So your homework is the one problem. It's this can problem again, accounting for the weights.